In this chapter, we will be learning about logarithms. In this lesson, we will be looking at applications of logarithmic functions. And we will begin by looking at the Richter scale.
So as it turns out, the Richter scale is actually a logarithmic scale. Okay, and so now what that means for us here is that every time you go up a level 10 here, now let's zoom in a little bit here. So every time we go up one value on the Richter scale, that represents an increase in a magnitude of 10 times, okay, in terms of the energy that was outputted by the output by the earthquake here. So if you go from a level 7 on the Richter scale to a level 9, because that's 2 steps on the Richter scale here, that's a difference of 100 times the size here. So this one here is 100 times the size of the level 7 earthquake, because it refers to the multiple of the amount of energy that's being released here. Okay, and when we talk about intensity, that's exactly what we're talking about, the amount of energy released. Okay. Now, take a quick look here. Look at our example. The earthquake in Guatemala in 1976, okay, was 7.5 on the Richter scale. Well, that was 10 times as strong as the earthquake in Italy in 1976. So here we go. And then here's Italy right here. Again, there's a difference in 1 on the Richter scale, so that means that this is 10 times larger. So basically, the further up you go on the scale here, really what's happening in terms of the amount of energy released is it's getting larger and larger and larger. Okay, so we use a logarithmic scale to basically pull that down, to pull that back down here, so that it's just a nice little scale. Now, to compare the earthquakes, we use this formula right here. Okay, so this is a comparative sort of a measure here. I naught is the base reference intensity for an earthquake. I don't exactly know what that is, but there's some event that sets out a bit of energy here. We call that the base event. I don't know what it is. It could be like a big guy jumping on the ground. I think at one point that I had read it was some weight of TNT exploding, but it sends out an energy wave in the ground. Okay, and we call that level 0. So now everything else is compared to that 0 level intensity. So when we take and divide those energies out, we take the log of it. That is now the magnitude on the Richter scale. Okay, so now if you're going to compare to, which is really what we're going to do in this course, we're going to compare two earthquakes here. What we do is we convert both to exponential form. So think about this. It's a common log. The base is 10. So 10, for example, in this case, to the m2. 10 to the m2 is going to equal that ratio, I2 over I naught. Okay, and the same thing for the first earthquake, the I1. So now that means we can rearrange those two equations there to solve for their specific intensities. And then we can find the ratio. Okay, so I2 over I1 is going to be I naught 10 m2 over I naught 10 m1. Okay, we'll zoom in a little bit more so you can see that. Now notice that these reference intensities are going to disappear when you're comparing two different earthquakes here, right? They're both compared to the reference intensity, and so when you compare them together, those things disappear. And when you're dividing powers, you're going to subtract exponents. And so this is the equation ultimately that we're going to use. Now I don't believe this equation is given to you when you write your exams. This is something that you'd have to memorize. In fact, you might even be given a different equation there altogether to work with, but this is really the one that's going to give you it's the most useful one, okay? So you might want to memorize that. Just before we go into some examples here, just a word of warning. You're going to get, in these questions, you're going to get dates, okay? You're going to, oftentimes what they'll do is then they tell you these things here. You're going to be told the number of people who died, okay, in these earthquakes. Granted, this is interesting information here, but these numbers are not relevant in this problem. I've seen so many people take the log of the date, okay, or the log of the number of people who died, and in these problems it's irrelevant. I mean, it's sad. Granted, I'll give you that, but it's irrelevant in the problem that you're answering. It's just extra information. So what you need to do here is we need to work with this equation. We are looking for a comparison of the intensities. In fact, you're never going to be even given the intensity. Okay, it means I can't think of a case where we've done that. Normally, what we'll do is we'll give you the comparison between how many times bigger this one is than this one, and then you'll be given a magnitude on the Richter scale that you're going to find. So it's either going to be that ratio or one of these measures right here that you're going to look for. Everything else is basically going to be extra material.
How many times more intense is an earthquake of magnitude 9.5 than one of 7.8?
So this first question here is just asking for the comparison of the two intensities. We are being asked what is I2 over I1. Okay, now we're given the two magnitudes here. We're given that the one earthquake has a magnitude of 9.5, okay, and the other earthquake has a magnitude of 7.8. So we're going to find the difference between those, okay, and so I2 over I1 is going to equal this, which is going to equal, well, what is 9.5 minus 7.8? Let me just make sure I'm doing the calculator because I don't want to make a mistake with that. And we get 10 to the 1.7. Now, that is actually not quite as useful as figuring out what that value is, and this is approximately 50 times. Okay, 50 times larger. It's 50.1, so approximately 50 times larger is what we're looking for right there. Okay, so I just went to my calculator to evaluate that. There's nothing really wrong with that as an answer, but it really doesn't give us a good sense of how big that is.
A major earthquake has a magnitude of 6.5 and is 723 times as intense as a minor earthquake. Find the magnitude of the minor earthquake.
All right. Now in this case, we are told what the comparison. We're told that I2 over I1, okay, the big earthquake over the little earthquake, if you want to think of it that way, we're told that ratio was 723. Okay, so we know that ratio here, and we know the magnitude of the larger quake. Now the larger quake was the one on top, right? Because this was 723 times larger than this one. So when we go to our equation here, we know that this is going to be 6.5. Now we're going to figure out the magnitude of the smaller quake here. Now take a look at this. The unknown is in the exponent. So what do? Well, I'm going to take the log. I'll take the log of both sides. So I'll take the log of the 723, and I'm going to take the log of this right-hand side here. Now, something wonderful is about to happen because we're taking a common log, and this is a power of 10. Well, this is log base 10 of 10 to this exponent here, which means those are going to cancel. So we're going to be left with the log of 723 is equal to, now we're just going to be left with the exponent. So there we go. So now it's actually quite easy now to solve for this magnitude. I'll bring that to this side and bring the log back over. So this will become, the magnitude is going to equal 6.5 minus the log of 723. And now that's just calculator work. 6.5 minus the log of 723. And we get that it has a magnitude of approximately 3.6. Okay, so that's the magnitude that we're looking for in this problem. Now before we leave the earthquake problems, just to take a little bit of a step back here, we've had two questions here, and we really only need to look at two of them because there's really only two questions you're going to get asked. You're going to get asked for the ratio of the intensities, or you're going to get asked for one of the magnitudes that we measure on the Richter scale. So it's either this I2 over I1, or it's going to be one of those two here. If it's this right here, you're basically just plugging in the information. Now, it might not be obvious to you in some of these cases what information is that you've got. Sometimes you're going to have to kind of think about what the problem is telling you, but this is basically what that'll boil down to. It's just determining what that ratio is. Same thing here. You'll be given the ratio of those two intensities here and one of those magnitudes in one way or the other, and then you got to solve for what's missing here. Now, in this case, this would require a logarithm.
Now we'll spend some time looking at the decibel scale.
Okay, another scale that we use that's measured on a logarithmic scale is the decibel scale. And actually that's a little bit of a misstatement there, because it's not actually the decibel scale, it's the Bell scale that really works like that. Okay, the Bell scale for measuring the volume of sound. However, when it comes to sound here, what we do is we we use the decibel scale, which is really just multiplying the bells by 10. Okay, we're using kind of a finer division. It's if you want to give it kind of a comparison that you're used to, it's like comparing centimeters to millimeters. Okay, so we're just going to use a slightly finer scale when we're measuring sound here. So we're going to use decibels. Now that means because we're using decibels here, it's a little different than the Richter scale. In the Richter scale, every time you went up 1 unit on the scale, that corresponded to an increase by a magnitude of 10 times. But here, slightly different. It's going to be whenever you go up by 10 on the decibel scale, that will correspond to a multiple of 10. Okay, so if you go, for example, from let's say 50 here to let's say 70. Okay, 50 to 70, that's 2 tens. Okay, that's going to be 10 times 10. That's an increase in intensity of 100 times. Okay, so that gives us, there's two formulas that you're going to use here. Now, I'll just zoom in on this a little bit here. So if you're using the Bell scale here, this is almost identical to, well, almost identical. It is identical to the Richter scale. Okay, when you're comparing the intensities of two sounds, that is going to be 10 to the intensity measured in bells up in your exponent here. However, if you're using decibels, what you got to do, it's the same sort of thing here. But what we're going to do here is when we take the difference in the decibels here, we're going to divide that by 10. Essentially what we're going to do is we're going to convert the decibels, back to bells by just simply dividing out that 10. And then we move forward from there. This is probably going to be the most useful formula that you're going to use when working with sound. Again, just like the decibel scale, you're not going to be given that equation. You're going to have to remember that. But it is worth remembering that and not trying to develop it from anything that you were given in the question.
A power saw at 120 decibels is how many times as loud as a telephone at 80 decibels?
All right. Well, I've not been given a lot of room to work here, but that's okay. So a power saw is 120 at 120 decibels is, again, how many times as loud as a telephone. Okay, we're given that information here. We're looking to compare them here. So we're going to take the intensity of the one, let's say the intensity of the power saw, okay, over the intensity of the phone. Now that will equal 10 to the decibels of the power saw minus the decibels of the phone all over 10. Okay, and so this is just a matter of plugging stuff in. So this will be 10 to the 120 minus 80 over 10. And you please remember to divide by 10. You've got to convert this back into the bells so that this is the exact same comparison as it was on the Richter scale. Now, but this is pretty straightforward. 120 minus 80 is 40. Divided by 10 is 4. So this is going to be 10 to the 4 or 10,000 times as large or times as intense. So the power saw, okay, power saw puts out 10,000 times as much energy into the air as a telephone.
How many more times as loud is the sound of piano playing at 67 decibels than a whisper at 22 decibels?
All right, so this next question is asking something really, really quite similar. Okay, we're going to compare the piano. Okay, how many times as loud is the sound of a piano playing to a whisper? Okay, and so we know, and we've got the decibel values here, so this is going to be 10 to the decibel value of the piano minus the decibel value of a whisper all over 10. And that will be equal to 10 to the 67 decibels minus 22 decibels all over 10. Whoops. 10. So then 67 minus 22, just think about it for a second, it's going to be 45. So this will be 10 to the 45 divided by 10, okay, or 10 to the 4.5. Now that's how many times louder the piano is than a whisper. But again, that's not a particularly useful number because it doesn't really give us a sense of how big this is. So you want to evaluate that in your calculator, and you're going to get that this is 31,000, approximately 31,600 times larger. It's a little bit larger than that, but just a little bit. That gives you a pretty clear, pretty clear idea of how much louder the piano playing is. So what that means is it's giving out
The threshold of pain is about 3,200,000 times louder than normal conversation. If normal conversation sits at 60 decibels, what is the level of the threshold of pain?
Okay, so this question wasn't specifically in the notes that I'm working from here, but I want to make sure that we've covered something like this anyway. Because there are two types of questions that you can get about sound. One is about the comparing the intensities, but the other one is about finding the measure on the decibel scale here. So now I've told you that the threshold of pain is about 3.2 million times louder than normal conversation. So what I've given you here is the intensity of the louder sound over the intensity of the quieter sound here, and we know that this is 3.2 million times louder. Okay, so now here we go. So this is going to be 3.2 million times louder, and that's going to equal 10 to the decibel scale of pain minus the decibel scale of a normal conversation, which which was given to us as 60 divided by 10. Okay, so now in this case here, the unknown, the thing that we're looking for here, is up in the exponent. So I'm going to use logarithms to get that out. So I'll take the log of both sides. So the log 3.2 million. Now, I'm going to try to take a little bit of a shortcut here because I'm going to take a common log of the right-hand side. Now, the right-hand side is a power of 10. So log base 10 of a power of 10 is going to leave us with just that exponent. So this is going to be the decibel level at the threshold of pain minus 60 over 10. And now, to solve for this, I will multiply first of all through by that 10. So 10 times the log of 3.2 million, and then I'm going to add the 60, because once I get rid of the 10, I've just got those two here. I want to get this term by itself, so I'll add the 60, and this will be the decibel level for pain there. So now I'm going to go to the calculator. This will be 10 times the log of 3.2 million, and then we're going to add that 60 to it. Oh, and so we're getting basically 125, just a slightly over 125 here. So this is approximately 125 decibels is how loud it is when it starts to get painful to listen to it. Okay, so anyway, so now you've seen a couple of questions here. One where you're looking for the intensity, the comparison of two sounds, and one here where you're using logarithms to find the level, the measure on the decibel scale. Very, very similar to what we did with the Richter scale. The only difference is that we have to end up multiplying by that 10, okay, to convert it to the Bell scale, and that is identical really to the Richter scale.
And finally, we will take a look at the pH scale.
So the pH scale is another example of a logarithmic scale, okay? This one here, though, can be a little bit confusing. You have to be careful when you read it, and I'll explain this in just a second here. But when you move, okay, 1 unit, okay, a single unit along the pH scale, that refers to a change in the concentration of the hydrogen ion by a factor of 10. Okay, you can see that down here if we zoom in a little bit on this. Okay, every step you take along the way here, we're talking about an additional power of 10, okay, in terms of the concentration. So we have this little formula that we build up here, and if you're a chemistry student at all, then you're very likely familiar with this formula, where the pH is going to be the negative log of the hydrogen ion concentration. Now I know there are other issues and blah blah blah, but just take it for what it is, okay? Just very simply, this is all we're looking at here. We're just really interested in the math of the whole thing. And in this case, the hydrogen ion concentration is expressed as moles per liter. Okay. Now, the issue here, or the complexity in this problem, comes from the description here. If we move down the scale here, we get more acidic. If we move up the scale here, we become more alkaline. So sometimes we can compare the acidity of two solutions, or we can compare the alkalinity of two solutions, and you have to pay attention to the descriptor here to know which direction you're going. for example, if we've got, let's just grab two here. If we've got two solutions here, we'll zoom in on this. Two solutions here who are at 4 and 5, okay? 4 is going to be, the solution at 4 is going to be 10 times more acidic than the one at 5 here, this normal rain, okay? Normal rain is 1/10 as acidic as whatever's sitting at 4 here. Now switch it around though. 5 is going to be 10 times more alkaline than whatever's at 4, or 4 is 1/10 as alkaline as whatever's sitting here at 5. So there's a few different ways to describe it. You just got to pay attention to what's being compared and what direction you're going here. Now my advice with this is to compare everything as if you're comparing acidity. Okay, because you can always reciprocate it if you're actually talking about alkalinity here. So, and we'll see an example of that in a little bit here, but let's just take a look at, let's say we've got two acids here, we're going to compare them. So what we're going to do is we're going to compare their hydrogen ion concentration. So here's our formula here. We're going to bring the negatives over in both cases. Okay, so the negative sits in front of the pH. And then because this is a common log in both cases, when we convert form, it'll be 10 to the negative pH. 10 to the negative pH is both equal to the hydrogen ion concentrations. Now, when we compare the two hydrogen ion concentrations here, okay, we get is going to equal 10 to the negative pH of the first one. Over here, 10 to the negative pH of the second one. And when we divide the powers here, now notice this looks very, very similar to the Richter scale equation and on the Bell scale. However, notice what's going on here. The first solution compared to the second solution, but notice that in the exponent here, the second solution, the pH comes first. Okay, there's been a reversal there. And that's because we have these negative signs sitting in front of those, the exponents there. So this became 10 to the negative pH of the one. Now minus negative the pH of the second solution here. So that turned that into a positive. So this is the formula that we want to use here when we're comparing acidity. And we'll take a look at some questions here, and then you're going to see an opportunity to apply this in just a couple moments.
Determine the pH of a solution with a hydrogen ion concentration of 3.4 times 10 to the negative 4 moles per liter.
Okay, so this first question is really just an application of the formula without any special change to it at all here. So the pH is going to be the negative log of the hydrogen ion concentration. So it's going to be the negative log of 3.4 times 10 to the negative 4, moles per liter. Okay, and this is going to equal, now I'm going to go to the calculator here. So this will be the negative log of, now 3.4, and I'm going to show you how to do this in the calculator here. Right here, this is what we're looking for. So we're going to go second, our comma button to get us into scientific notation here, and I'm just going to plug in the negative 4. There's my exponent. So this right here means the same as 3.4 times 10 to the negative 4. Close the brackets, press enter, and there we go. Our pH is roughly 3.5. Okay, so approximately 3.5. Now, just to show you that that is exactly what I said it was, just in case you've never seen that before, if we went negative log of 3.4 times 10 to the negative 4, close the bracket. Whoops, what did I do wrong? Oh, I'm sorry. That's right. Yeah, actually, that's a good point to mention there. What I did wrong here is I used the subtraction button without thinking about it right there when I meant the negative sign. Okay, if you get an error like that popping up and you're pretty sure you've done anything correctly there, in a lot of cases, what's happening here is you're using the wrong button for the negative sign there. If I press enter now, there we go, 3.5 once again. So just to show you that there's a couple of ways that you could enter that in on your calculator.
A soft drink has a pH of 3.4. What is the hydrogen ion concentration of that drink?
All right, so in this case, we're just being asked to go backwards here. So the pH is equal to the negative log of the hydrogen ion concentration. In this case, we know that the pH is 3.4. So it's negative log hydrogen ion concentration. So bring that over, bring the negative over. We get negative 3.4 is equal to log of the hydrogen ion concentration, and now we're going to convert forms here, and remember that this is a common log. So the concentration of the hydrogen ion will be 10 to the negative 3.4 moles per liter. Now, except that you're not going to see it written like that. Okay, they wouldn't do that. They're going to put this in scientific notation here. So what we're going to do here is go to our calculator. We're going to enter that in, 10 to the power of negative 3.4. And we get, what is it, 3.98. And this back here means times 10 to the negative 4. Okay, so approximately equal to 3.98 times 10 to the negative 4 moles per liter. There you go.
How much more alkaline is seawater with a pH of 8.4 than pure water with a pH of 7?
Okay, so now here's a question where we're being asked to compare alkalinity. Now, what I'm going to do here, though, I'm just going to compare acidity. We're going to start with acidity. Okay, we're going to use that little formula that we developed before here. We're going to compare the acidity first here. So I'm still going to compare seawater to pure water. Okay, seawater to pure water. So we're still going to, what are we going to do here? We're going to take the hydrogen ion concentration of seawater. We're going to compare that to the hydrogen ion concentration of pure water. And that is going to be 10 to the 8.4 minus 7. Okay. Oh, sorry. My mistake. Because remember what our formula had that flipped around here. This is going to be the pH of pure water minus the pH of seawater. That's how that works here. But I'm going to stick with that first here. This is the equation that we used here. We're comparing seawater to pure water, okay? But we're comparing the acidity, okay, of seawater to pure water, and then in our exponent it's going to be pure water minus seawater. That's the formula that we built here. So this is going to be 10 to the 7 minus 8.4. Okay, so 7 minus 8.4 is going to be negative 1.4. So 10 to the negative 1.4. Whoops. Now, okay, think about what this means here. This is, actually we can evaluate that. Watch what that means here. This is 10 to the power of our answer there, negative 1.4. So this is how much more acidic seawater is than pure water. Okay, now it's this small decimal here. Now, if we want to know how to compare alkalinity, what we're going to do is we're going to reciprocate that because we're going in the opposite direction here. So this is comparing the acidity here. So to compare the alkalinity, I'm going to reciprocate it. So therefore, seawater, okay, is 1 over 10 to the negative 1.4, or simply 10 to the 1.4 times more alkaline. Now I'm running into my next question here, but anyway, more alkaline. And we can evaluate that. Okay, 10 to the 1.4. So it's basically 25 times more alkaline. It's approximately 25 times more alkaline. Okay, so just think about that formula here. Sorry, add it over here. Think about this formula here. This is when we're going to compare the acidity. We are comparing the acidity. So the whatever the solution is, okay, what are the two that we're comparing here? We're comparing one to the other, comparing solution 1 to solution 2. Every time we use this formula, we're going to be comparing acidity. If you want to compare alkalinity, you're simply going to reciprocate your answer. I think that's probably the easiest way to go about doing this.
Compare swimming pool water with a pH of 7.5 to seawater with a pH of 8.4.
Okay, so this one kind of leaves it open here. We're going to compare swimming pool water to seawater. So if we use the formula we built here, we're comparing acidity. So let's do that. So we've got the we're comparing pool water to seawater, so we're going to put pool water up top, and we will put seawater down below. But that means this is going to be 10 to the pH of seawater minus the pH of pool water. So this is going to be 10, and the pH of seawater is 8.4, minus pool water, it's 7.5. Okay, so what is that? 8.4 minus 7.5 is going to be 0.9. Okay, and now to figure out what that value is, how many times more acidic it is, we're going to take 10 to the power of 0.9. And we're going to get basically, well, okay, we'll route it here, make this approximate, 7.9 times, okay, more acidic. Okay, so the pool water is 7.9 times more acidic than seawater. Good, that's exactly what we wanted to compare here. Now we could compare the alkalinity if we wanted to, but this is good enough here. It didn't tell us exactly how to do that. The formula that we developed compares acidity. Remember, if I wanted to compare the alkalinity, I would just reciprocate my answer. There you go.